All right, how'd the homework go? Anybody have any questions about any of those problems? Yep.
Yeah, number 6.
Okay. You want to just go through it?
Yeah.
Yeah. Um, so number 6. This is one of the few problems that I make you do a unit conversion on. So let me see. 2 miles per hour is about 4.47. Oh no, I'm going the wrong way. Miles per hour to meters per second. So I want to 2 times 16. So this is about 0.894 meters per second. And then this one is about 1.788 meters per second. So the first thing you have to do is that. This ball rolls down the incline. When it reaches the point A, it has a speed of, so it's going down this way. When it reaches A, it has a speed of 0.894 meters per second. When it reaches B, gravity's making it speed up that whole time. And at B, it has a speed of 1.788. And so it says, first we're going to choose our 0 position to be at A. The positive direction down the ramp. So positive is this way, negative is this way. And we don't know the distance between them. I mean, basically, like in both parts of this problem, we're trying to figure out something about the distance between them. But it says, what's the position of the ball at B? So that's what we're looking for here, the position. We're going to choose our time equals 0 instant to be when the ball passes the point A. And our time final instant to be when it passes B. How do you know when to choose your instant time 0 and time final? It's kind of always the same thought process. You're asking yourself, what's an instant where I either know stuff or I'm trying to find stuff? Okay. We know stuff at A. We're given the speed. We're told that we're using that as the 0 position. And we're trying to find something, the position when it passes B. And so that's how we choose those 2 instants in the stopwatch. And always time equals 0 is before time final. Okay. So let's start listing these variables out. And I try to always do them in the same order. So my order is time final, acceleration, P initial, P final, V initial, V final. Do we know how long it takes to get from A to B? 3 seconds, yep. So we do know that the stopwatch, when we click it off, says 3 seconds. Do we know the acceleration? No, there's nothing that gives us the acceleration. Do we know the position at time 0? So remember, time 0 is when it passes A. So do we know the position there? 0, yep, exactly. So this is a simpler idea than coming up with the right wording for it, I've found. But anytime your time equals 0, no, sorry. Anytime your position equals 0, okay, is at the object's location at time equals 0, okay? That is setting your initial position to 0, okay? So anytime you just say, I'm going to call my position equals 0, where the object is when I click the stopwatch on, that's setting this P initial to 0. We're trying to find P final. Do we know the velocity at time 0? That's right, it's 0.894, and you also remember, so it gave it to us as a speed, so then you also have to think about the direction. So it's going to be plus or minus 0.894. And then you have to think, is it moving in the positive or negative direction? In this case, it's positive, so we want the positive. And then our V final is plus or minus 1.788. I don't know why I randomly kept 3 decimal points. I always keep 2. I'd randomly, but that's the kind of thing you can do if you don't care about significant figures, and I don't. Try it, it's so freeing. So now we have to figure out the direction. Is it moving in the positive or negative direction? Positive still? Okay, so there we go. Now, is there any one of those 3 equations that works for this set of variables? There's not. And the reason is that every one of those 3 equations has acceleration in it, and we don't know the acceleration. And we're not trying to solve it. So nothing is going to work in one step. And so I said that when that happens, you should try to find an equation that'll let you either solve for time final or acceleration. We already know time final, so in this case, we want to solve for acceleration. Okay, so what equation will let us solve for acceleration? It looks like this one will. Because we're trying to find A. VF we know, VI we know, and TF we know. It's possible something else would work too, but if this one works, it's the simplest one. You always want to use it. So now I'm just going to plug in the values. 1.788 is equal to 0.894 plus A times 3. And if you subtract 0.894 from both sides, you get 1.78. Nope, I'm subtracting. So you get 0.894 is equal to 3A. And so A is equal to 0.298 meters per second squared. All right. There's one sort of sanity check we can do at this point. You're always sort of looking for ways to convince yourself something's right, that everything's right, or that something's wrong. So in this case, now we've figured out that the acceleration is positive. And positive, we said, is down the ramp, okay? So the acceleration is positive. The velocity in the whole time is positive. So is this speeding up or slowing down? Speeding up, and does that make sense with what's happening physically in the problem? Yeah, so that's a good sign. Okay, so, and then it asks to sketch a position versus time graph. So we can, so we know that it's going from position 0 to position, oh God, I didn't even finish this problem, sorry. We got the acceleration. We're not trying to find the acceleration, we're trying to find P final. But now we can get another equation that lets us solve for P final. So what works now? This one. And now, we can check it. We're looking for P final, and it's in here. And then everything else, P initial, we know. V initial, we know. Time final, we know. Acceleration, we know. So this equation will work. Okay, so P final is equal to 0 plus 0. What was it, 894? 0.894 times 3 plus 1/2 times 0.298 times 3 squared. And so P final and I get 4.02 meters. Okay, let's sanity check this. Does it make sense that that's a positive number? Well, A is 0, and B is in the positive direction from 0, so yeah, we expect that to be positive. So that, again, makes sense. Okay, so now I'm going to do the position versus time, sketch this out. The times that we know about are time 0 and time 3 seconds. And the positions we know about are position 0 and position 4.02. And so we know it's going to start here and end here. And now let's think a little bit about the shape of this. We know that the acceleration is positive. So if there was no acceleration, it would just be a straight line between these two. But we have a positive acceleration, which means that it's going to be concave up, okay? Then we can also say, do we know anything about the slope at this time equals 0? Remember, the slope represents the velocity, and we know that it's positive. So I can start it out with sort of like a shallower positive slope, and then give it a concave up shape like that, and it'll look something like this. I think really the way it asked for this was, it said, sketch a position versus time graph like you did in numbers 2 and 3. So in those problems, you're not thinking about acceleration or anything, so a straight red line is fine. But if you can add those other details, that's even better, you know. Okay, so now we're going on to part D. And we're going to choose the 0 position at B, positive direction up the ramp. And 0 again, time is when it passes A. So none of this changes anything about the motion. The ball still does the same thing. But now our 0 position is here. And our positive direction is this way. I'm still going to choose my time equals 0. To be when it passes the point A. And my time final to be when it passes B, because those are still the instance where we know stuff and where we're looking for stuff. And now I'm going to list out what I know and want. Time final is still 3 seconds. We still don't know acceleration. I mean, just like we didn't before. Our initial position, okay, now we've chosen our 0 position to be at B. So before we start this problem, we don't know what the position is at time equals 0. Well, we just did this problem. Yeah. So, but I guess when I wrote this question, the idea was that you redo it sort of from scratch, like you didn't already do those first parts, and just look at what you get the 2 ways, you know. So what we're trying to solve for now is the position when the ball passes A. We know that the final position is 0. The velocities, so the initial velocity, okay, we know the speed is 0.894. But now the ball is going in the negative direction, okay? So our initial velocity is negative 0.894. And our final, with the same thinking, it's going in the negative direction, and it's 1.788. And now we'll use the same equations to solve this as we did before. So first I have to get the acceleration with this. So that says negative 1.788 is equal to negative 0.894 plus 3a. And so that says negative 0.894 is equal to 3a. And so a this time is equal to negative 0.298 meters per second squared. Does that contradict what we got in the first part? Because we got positive 0.298 last time. This time we got negative. It actually says the exact same thing as what we got in the first part, because last time we got a positive value that meant down the ramp, okay? This time we got a negative value, but this time negative means down the ramp. So either way, the acceleration is happening down the ramp in the same direction as the velocity, which says this thing is speeding up, okay? And now we can go to this one. PF is equal to PI plus VI TF plus 1/2 A TF squared. So 0 is equal to PI plus negative 0.894 times 3 plus 1/2 times negative 0.298 times 3 squared. And what you, this should be a negative 0.298. And what you get here is that PI is equal to positive 4.02 meters. And does it make sense in this case that A is a positive number? Yeah, because if you start at the 0 at B and move in the positive direction up the ramp, you're going to get to a positive position. Okay. And then it asks some stuff about do these answers agree with each other? Well, they both tell the same basic story. The basic story is these 2 points are 4.02 meters apart, and the object is moving down the ramp and speeding up down the ramp. Okay. Any questions about that one? Any other homework questions you'd like to see? Yes?
7.
Okay. Okay, so it's going 45 miles per hour, which is, so 45 times 16. This is about 20.11 meters per second. Everything else is already in SI units. And if I draw a picture of this, let's say the car is going this way. I guess I'll draw the path of the car here, because remember, the location of the car at any instant is where its center of mass is. So we'll start here and end here, and the distance between those is 30 meters. When it's at this point on the left, the speed is 20.11. When it's at the spot on the right, the speed is 0. It's at rest. So let's choose a 0 position here, a positive this way, a negative this way. You don't have to do that, but most people would do that, I think. And then our time equals 0 instant is when the car hits the brakes. And the time final is when it reaches rest, when it finally stops. And then we'll think about what values we know and want. Okay, do we know how long it takes in time? Do we know what the stopwatch says at the end of the motion? No. Do we know the acceleration? No, that's what it's asking for part A. Do we know the position at time 0? We do. What is it?
30 meters.
At time 0, it's 0, because that's where we, but yes, our P final is 30 meters. And we know that because if you start at 0 and go 30 meters in the positive direction, you get to positive 30. Do we know the velocity at time zero? Well, we know the speed is 20.11. Is it moving in the positive or negative direction? Positive, so we want the positive. And then V final, what's that? 0 when it comes to rest, yep. So the equation that works here will be 2 times A times the quantity P final minus P initial is equal to V final squared minus V initial squared. And you can see that because A is in it, P final is known, P initial is known, V final is known, V initial is known. Yeah, I wrote it down wrong. Thank you. 30. Okay, so 2 times A times the quantity 30 minus 0 is equal to 0 squared minus 20.11 squared. And so that says 60A is equal to 404.69. And divide both sides by 60. Oh, I missed something important here. The negative sign. So you square that number, but there's still the negative sign in front of it. So divide both sides by 60 and you get that A is equal to negative 6.74 meters per second squared. Okay, so let's think about whether that makes sense. Our acceleration is negative. What direction is our velocity during this motion? What's the sign? Positive. So velocity and acceleration having opposite signs means it's slowing down. Does that make sense with what's physically happening in this problem? Yeah, so that's good. And if I would have not noticed that I missed that negative sign, that's where I would have caught it. I would have gotten an answer of positive 6.74. I would have then compared that to my velocity and said, that means it's speeding up. That's not how this is happening. Okay. Yes?
For both, sorry, because I came a little late. Can you write, to go up a little bit?
Yeah. Miles per hour to meters per second?
Yeah, 45 to 20.
Yeah, so that's 45 miles per hour. So I wrote it, yeah, that's how I wrote it. And 1 mile is 1609.344 meters. And 1 hour is 3,600 seconds. Okay, that is part A. So what's the car's velocity now when it had traveled 15 meters? Okay, this is something we haven't seen before. So this was part A. But now for part B, this is the first time where our choices for part A, for time equals 0 and time final, will not let us solve part B. We're going to have to choose at least one new one, okay? And that's because if any question asks about a specific instant, that has to be one of your two instants. And we didn't choose a time equals 0 or a time final at the instant when the car had traveled 15 meters, okay? So I'm going to, really you could set it up with it as your new time equals 0 or as your new time final. I'm going to set it up as my new time final. So my time equals 0 is still going to be when the car hits the brakes. but my time final now is going to be when the car has traveled 15 meters. And my P equals 0 and my positive direction are going to stay the same. There's no reason we have to change those. So now we have to think, you know, if you keep those two the same, then everything you knew before, you know again. Or if you keep all four of them the same. But we've changed one of them, so we should think about this again. Okay, so we don't know how long it takes. We do know the acceleration. We just figured that out. So the acceleration is negative 6.74 meters per second squared. The initial position, we still know is 0. I'm still using the same position equals 0 location. P final. So in this case, now that our time final is when it's traveled 15 meters, if you start at 0 and travel 15 meters in the positive direction, you're at a location of positive 15 meters. The initial velocity is positive 20.11 meters per second. And this time we're trying to find VF. There's no time here, so the only equation that could work is the one that has time in it. The one that doesn't have time in it. So 2 times A times the quantity PF minus PI is equal to VF squared minus VI squared. It has VF in it. PF, PI, and VI are all known, so this will work. So 2 times negative 6.74 times the quantity 15 minus 0 is equal to VF squared minus 20.11 squared. So if you multiply this first stuff all together, you get negative 202.2 is equal to VF squared minus 404.69. Now add 404 to both sides. And you basically get, so positive 202.49, that's just round off error, those really should be the same, is equal to VF squared. Okay, and now here's the other thing that you haven't seen in a problem yet, I don't think. So now we're going to take the square root of both sides. And I think if your experience was like mine when I started physics, you had been in math classes before where you were sort of vaguely told if you take the square root of a variable, you have to consider the positive and negative answers. But it's a little abstract. Well, in physics, we're going to have to do that, and each one of those two things means a physically different thing. And in a lot of cases, you're going to have to decide which one makes sense based on which one makes physical sense with the problem. Okay, so if I take the square root of both sides, I get VF is equal to square root of this. So square root of 202.49. And you get plus or minus 14.23. Well, is this car moving in the positive direction or the negative direction? Positive, and so this is our answer. Any questions about that? Okay, and then it says, just to get you used to sort of thinking in terms of directions, thinking of velocity and acceleration as directions, it says draw the direction of the velocity during motion. So that's this way. The acceleration, we figured out that the acceleration was negative. So the direction of the acceleration is this way. Any questions about that one? Any other homework questions? Okay. So now we're going to start applying this constant acceleration stuff to free fall and projectile motion. So free fall and projectile motion. And there are 4 times during this class where I'm going to tell you, so, you know, this class is all about things rolling and falling and being thrown and where does this land and whatever. It's all stuff you've seen in your life, you know. And so you have opinions on all this stuff. And most of your opinions, your intuition about stuff is helpful, okay? It's probably the biggest reason why this class tends to be easier for more people than Physics 2, which is like electricity and magnetism, because you can't hold that stuff. It's hard to have intuition about it. But there are a few places where your intuition in this class are going to lead you astray, most likely, for most people. And so I'm going to try to point those out. There's these 4 of these places that I'm going to call common misconceptions. And this is the first one. So common misconception number 1. So it's often thought, this is a very common thing for people to believe. And if you believe this, or if this is how you think about it, you're in really good company. Like the best scientists in the world thought this until the 1700s, but maybe the 1600s. Anyways, that gravity makes heavy things fall faster. Okay, so, and your experience from this comes from stuff like if you dropped a truck from the same height that you dropped a feather, the truck would hit the ground before the feather. And you're like, okay, the feather is light and and that's why it flutters down while the truck smashes down. Actually, though, gravity by itself makes all objects fall exactly the same. So gravity makes all objects fall with the same acceleration. And by the way, that acceleration on the surface of the Earth is 9.81 meters per second squared down.
That's the acceleration of the Earth.
That's the acceleration of objects, yeah, like near the surface of the Earth. Yep. And if you did the same, if you dropped objects on the moon, it would be different because of different gravity. When objects do, when objects in free fall do fall with different accelerations or fall at different speeds, when they do fall differently, it's just an effect of air resistance. Okay, so the reason that a truck and a feather fall differently is because there's different interactions between the feather and the air than there are between the truck and the air. Okay, it doesn't have anything to do with gravity. So I'm going to show you a video that's, I think it's pretty amazing. So what it is it's this big building where they have the ability to evacuate all of the air out of this building, this huge amount of air. They said it's tons of air. Like if you weighed that air, it's tons of it. And they're able to pump almost every single molecule of the air out. And so this thing is just a giant vacuum with no air in there to cause any effects. And then, so before they pull all that air out, they drop a bowling ball and a feather, and it does exactly what you'd expect. The bowling ball smashes down and the feather flutters down slowly. But then they suck all the air out of it, which has to be very expensive, and they do the thing again, and you're just going to see these two things falling down exactly the same. The one thing that's, I don't know why they never show it at full speed. They only show it in slow motion. So they show it in slow motion so you can see it's exact. You can see the feathers aren't rippling or anything. But it would be nice, I think, to see the feather just slam down to the ground, So anyways, let's watch that. So that's crazy. So that's how effective it is at getting all the air out. Like this building has 30 tons of air inside, and when they're done pumping it, there are 2 grams left. I don't know how they measure that. Uh, is there air in this now or not? How can you tell? He's alive, correct. Okay, very good. There's no fluttering because air is what makes feathers flutter, you know? They just move like they're made out of steel. Okay, so let me give you a list of what are the things that determine the air resistance effect on an object's motion. Like, how can you guess when air resistance is going to affect something's motion too much to trust your calculations? Okay, what determines the air resistance effect on an object's motion? Okay, before I go into these, I mentioned the helicopter thing. I don't know, you know, like mountain climbers on really high mountains, it's very dangerous. It's very cold, and there's a lot of dangerous stuff, and the air is very thin, so it's hard to breathe, and you know, people die on the world's highest mountains pretty often. And you might think like, how can people like in this day and age, how can you die climbing a mountain? Like, why don't they just send like a helicopter up to get them, you know? But the thing is, the mountains are so high that the air is super thin. You know, the air is like a third the density of air at sea level. And it gets so thin that helicopters just are not even capable. It's not a functional machine anymore at that height. So like helicopters, like at Mount Everest, even the base camp of Mount Everest is pretty high altitude. Helicopters can get to base camp, sometimes a touch higher, but any higher than that, it's just you. There's nothing that can get you down, you know. Okay, so the first thing that determines the effect of air resistance on an object's motion is the object's mass. Okay, so you're not crazy. There is definitely like a correlation between mass and how fast something falls in our experience. So if everything else is equal, all else equal, a heavier object will fall faster than a lighter object. That's if they're the same shape, roughly the same surface, you know, that kind of stuff. So a heavier object falls faster than a lighter object. An example of that would be like, imagine a metal pinball that you drop at the same time as like a ping pong ball. They're basically the same shape and size, but if you drop them from more than just a couple feet, they'll hit the ground at noticeably different times because the air resistance will slow down the ping pong ball. Second is surface area. So again, with everything else being equal, an object with less surface area will fall faster. There's a little more complexity to it than that, but let's just call it that for now. It's an easy thing to keep in your head. So an example of that would be like, imagine a G.I. Joe that you drop at the same time as a GI Joe with a parachute. You know, the parachute doesn't really weigh anything. These two things have the same mass, but that parachute is designed to have a really big surface area that catches a lot of air, and that's why something in a parachute descends really slowly. And then the last one, and the one that has the biggest effect on it, is the object's speed. This one, so let's say this one is extra important. All else equal, a slower object, that doesn't make any sense, hold on. Let me word it like this. Everything else being equal, a faster object has more air resistance than a slower object. And so like when I said the thing about dropping a pinball and a ping pong ball, if you drop them both from here down to the table, they'll hit at about the same time because neither of them is accelerating long enough to get up to a very high speed. And so neither of them has a lot of air resistance. But if you go up to 10 feet or something, they build up enough speed that the ping pong ball's motion is affected a lot by air resistance. And so one thing to keep in mind is that it isn't just a matter of the object. Does the object have a lot of air resistance? It's also the application, you know? Like, does a baseball have a lot of air resistance? Not if it's moving 5 miles per hour or 10 miles per hour, but if it's moving 100 miles per hour, it does, you know? If you ever watch the Tour de France, you see this in a really obvious, exaggerated way. I said that speed is extra important. That's because in calculating the air resistance, speed is the one that's squared in the calculation. And so small differences in speed lead to big differences in air resistance. So like in the Tour de France or big like multi-day bike races, the two most important kind of days are time trials and races through the mountains. Those are the two places where you can make up a lot of ground. And when people are racing in the mountains, you know, they're going up big hills, you'll see what they're wearing are just like regular biking shirts. A lot of times they'll be wearing biking caps, you know. Their shirts will be totally like unzipped just to stay cool and stuff. It's like they'll be up on the top of their handlebars like they're making no effort at all to be aerodynamic, okay? That's when they're climbing up a mountain. When they're in a time trial on the flat, they'll be in a suit that looks like it's made out of rubber. Their helmet is like a teardrop shape. They never get out of this position like this. Everything they're doing is about air resistance more than it's about like their physical, you know. The number one thing they're working on is aerodynamics. And the difference is just simply that in the mountains, they're going 15 miles an hour. And when they're in the time trials, they're going 35 miles an hour. And that difference in speed is the difference between air resistance making no difference really and being everything, you know. Okay, so now we're going to start applying the constant acceleration equations to free fall and projectile motion. There are two facts that I want you to keep in mind that are going to come up in problems pretty often. So two useful facts for 1D free fall and projectile motion problems. So the first one is that if an object is dropped, so like if any problem says an object is dropped, its starting velocity is the same as the velocity of what it's dropped from. So if it's a little harder to come up with one-dimensional examples of this, so I'm going to just think of a car, which is kind of a two-dimensional motion. But if you're driving in a car and you have, you know, anything in your hand, it could even be a balloon or whatever, and you hold it out the window and let go of it, at the instant it's dropped, the velocity of that ball is 60 miles per hour, or whatever the velocity of the car was. Okay, so on the other hand, if something is dropped from a bridge or a building or whatever, good bridges don't have any velocity. That's one of the key qualifications for being a good bridge. So at the instant you let go, the velocity is zero. It's at rest. And the second one is if the object is launched up or thrown up, when it reaches the highest point in its flight, the velocity is zero. So with this one, if you ever have a problem mention something about the highest point that something goes, you're just waiting to use the fact that the velocity is zero. You'll always use that. You can think of that as like the definition of the highest point for us. Okay. Okay, let's do an example. So let's say that you're on a lowish bridge and you're curious how high it is. So you don't have a long enough tape measure with you, but you have like a rock or something and a stopwatch. Don't do this if there's boats coming. And so you drop the rock and it takes 1.2 seconds for the rock to hit the water. How high is the bridge? So this is a free fall projectile motion problem, but the approach is exactly the same as every other constant acceleration problem. I'm going to choose a zero position and a positive direction. And for these, I'm just always, I think it's helpful to always choose those kind of the same way. So I'm always going to choose my zero position at the lowest spot in the problem. In this case, it's the water. In a lot of problems, it would be the ground. And I'm going to put my positive direction up. And now we have to choose the two instants. So I'm going to choose my time equals 0. This one actually has a stopwatch in it, so the time 0 and time final correspond to when you really click the stopwatch. So time equals 0 is when you turn the stopwatch on. And the time final is when you turn it off. That's when it hits the water. And let's list out what we know and what we want. Do we know time final, how long it takes to hit the water? Yeah, that's right. So yeah, 1.2 seconds. Do we know the acceleration? That's right. And since we chose our positive up, it's going to be negative 9.81. And so free fall problems, that's the one thing. If something's in free fall or projectile motion, you always know the acceleration. So negative 9.81 meter per second squared. Do we know the initial position? Not yet, right. That's what we're trying to find. We want to figure out what the position is at the top of the bridge. Do we know the final position? 0, yep. So PF is 0. Do we know the velocity at time 0? It's that velocity of what it's dropped from things. So this is dropped from a bridge, a good bridge, hopefully, so velocity initial is 0, right? Do we know what the velocity is right before it hits the water? No. So this is the complete list. Is there an equation that works with these? I think probably this one will. PF is equal to PI plus VITF plus 1/2 ATF squared. It has PI in it. Everything else is known. So yeah, this one will work. So now plug in these values. 0 is equal to PI plus 0 times 1.2 is 0 plus 1/2 times negative 9.81 times 1.2 squared. And you get 0 is equal to PI minus 7.06. And so solve for PI, and you get that the bridge is 7.06 meters high.
Sorry.
Period. Yeah. Any questions about that? Okay, so well, we got a couple minutes. Let's do one more, answer one more question about this one. Let's say we do want to know what the velocity is. Like, let's say we want to know if it would be safe to do this if you don't know that a boat's coming. Like, what would this thing do to the boat? Okay, so we want to know the velocity when this thing reaches the level of the water. And you can always think of this as what's the velocity the instant right before it makes contact with the water or the ground. So you don't want to think it's the instant right after it made contact, because that contact will change the whole motion. Okay, it's right before. So what's the velocity just before it hits the water. You could also think of it as like, imagine there's no water there. What would be the velocity when it reaches the level of the water? Okay, is there any reason that we have to change our time equals 0 or time final? No, the instant that I'm asking about is still one of our two instants that we chose before. So we're going to use the same time equals 0 and time final. And that means everything we knew before, we still know. So time final is 1.2 seconds. Acceleration is negative 9.81 seconds. P initial, now we know, we solved for that, is 7.06 meters. P final is 0. V initial is 0. And we want to find V final. There are two equations we can use for this one. We know a lot of information, that's why we have more options. One of them is this one, and so really that's the end of the story. If you can use this one, use it. But I want to show you what happens with the other one too after I'm done with this. So V final is equal to 0 plus negative 9.81 times 1.2. And so you get that V final is equal to negative 11.77 meters per second. Does it make sense that that velocity is negative? It's not the location, it's the direction when you're talking about velocity. And so since we chose our positive direction up, and this is moving down, it needs to be negative. Okay, so now what if we didn't notice that this equation works? This one does too. So what would happen if we use this one? So now we go 2 times negative 9.81 times 0 minus 7.06 is equal to V final squared minus 0 squared. And so you get 138.52 is equal to VF squared. And now we're going to take the square root of both sides. Okay, but this is where I wanted to show you this because this shows what happens if you're not careful about those signs. If you take the square root of this variable, the answer can be the plus or the minus square root. Okay, so our V final is equal to plus or minus 11.77. And now in this problem, the only way for you to decide is to think about what direction the object is moving. Okay, in this case, we chose our positive direction up. The object is moving down, so we know that this has to be negative. Any questions about that? Okay, I'll give you a couple more problems like that to work on over the weekend. And if you have trouble with any of them, feel free to bring them on Monday. And we're just going to do example problems now for a couple days.